This week I was making some measurements of Wu cohomology for manifolds, and it's very clear all the measurements indicate that there is a way to get from the Betti numbers of the manifolds, the usual simplicial cohomology Betti numbers. You can get to the Betti numbers of the higher order characteristic of this Wu characteristic. I cannot prove that yet, but I will just show one example where we see kind of all the details of the computation, and the rest is just, this is numerical. I see this, I cannot prove it yet. I think it's exciting because I think there is a kind of a natural chain equivalence or homotopy between these complexes. But first of all, just about the definition. So we have a down-to-earth cohomology, which is the simplicial cohomology, and I'm using the approach of Ekman from 1944, which is using the Hodge approach. So the cohomology is just the kernel of some explicit matrices, and the dimension of the kernel, these are the Betti numbers. Very down-to-earth, 4 or 5 lines of code can compute this. This needs a little bit more, maybe a couple of lines more code. I have put that also on the website. You can compute this cohomology. Also the matrices are just much larger in general. So here this is the computation of the smallest manifold which exists, right? The smallest discrete manifold has just 4 points. It's a one-dimensional manifold, a one-dimensional circle. So here this is the Dirac matrix of the, for the simplicial cohomology, and this is the Laplacian, which is just the Kirckhoff Laplacian here. This is also the Kirckhoff Laplacian, it's just a dual, is the same here, and so this L0 and L1 in this case are the same. We have, of course, we have these constant functions on vertices which are in the kernel, because the things sum up to 0. And here also, these are the one forms which are realized by, closed loops in this circle. So this is the computation of the cohomology in the case, the usual simplicial cohomology. This is the computation in the case of the Wu cohomology, where we look at pairs of simplices. So it's the same, kind of almost the same setup. It's just a delta set. So I have a little bit of abstract nonsense here in a Mickey Mouse setting. So delta sets, a big fan. Delta sets are nice because the set of delta sets forms, or finite delta sets forms topos, and like the set of sets. So the set of sets doesn't have geometry, but the delta sets have geometry, they have cohomology, they have content, they have calculatory, they have curvature. There's everything which we really want is there. Even a kind of here, this is a Mickey Mouse Atiyah Singer or Mickey Mouse Atiyah bot. It all works very well. So we have the cohomological definition of Euler characteristic is the same than the combinatorial definition, and also for the Wu characteristic and the higher Wu characteristic. Also for any level this works. You always have the same setup, and the proof is very simple in that McKean-Singer symmetry. The supersymmetry gives you the super trace of the heat kernel at t equal to 0, gives you the combinatorial definition, and for t equal to infinity, where all the kind of things have been washed away, which is non-zero eigenvalues, the positive. These are positive eigenvalues, right? The non-zero eigenvalues have positive because it's d squared. So whenever you have a Dirac operator, Dirac matrix, which you have in a delta set, then this equivalence holds. And then additionally what you can do is you can push all these combinatorial data from the simplices to the vertices, and that gives you curvature. Or indices, if you push it just to one point, then you have the Poincare hop, then you have indices, integer indices. In general, if you distribute it, you get curvature. So this is a very, very simple kind of result. And there is also a dynamical version which I like very much. When you have an automorphism or a morphism on the structure, then you have a dynamical version. So we have a dynamical version of Euler characteristic, which is the Lefschetz number, cohomologically defined or combinatorically defined, and it's the same. That's actually then the Lefschetz fixed point theorem, which generalizes the Brouwer fixed point theorem if the cohomology is trivial. So it's very kind of down to earth, really Mickey Mouse stuff. But here is the computation, and here's the computation in the simplest case. Maybe I put the code up. So what we have is kind of in this interaction case, we don't look at simplices like here. These are simplices. They're zero-dimensional simplices and one-dimensional simplices. What we have here is we have pairs of zero-dimensional simplices which interact, pairs of zero and one-dimensional simplices which interact, and then pairs of one-dimensional simplices which interact. So these are this produces then also a delta set, right? A set of sets, kind of, and we have phase maps which are then defining this exterior derivative. So we have a calculus, we have Stokes, of course, we have all the calculus in general. So any delta set automatically has all this structure. So in any delta set, we have a Mickey Mouse Atiyah Singer and we have a Mickey Mouse Atiyah Bott result. And I certainly say more about this in future. But for now, I kind of struggle to try to kind of get here a grip on these measurements. So these are measurements. Mathematics usually doesn't appreciate measurements, right? In chemistry or whatever other sciences, if you make measurements, that's a big deal. In mathematics, it's nothing. So we need to prove this. We need to kind of have an equivalence between, you know, the forms here and the forms here. And at the moment, I have no idea how this is going to work. That's it for today.